Question number 6, figure number 8 shows a longitudinal wave. The different parts of the waves are already mentioned. The particles are very close to each other. This part of the longitudinal wave is called compression. Where the particles are comparatively away from each other, that part of the wave is called rarefaction. So 6.1 is an AO1 question. What do the label A and B on figure number 8 represents? Choose the answer from the box. Amplitude, frequency, refraction, reflection, and wavelength. We know that the point number A is showing the particles of the medium are away from each other. This part of the wave is called rarefaction. Whereas B is the midpoint of two consecutive compressions, it is called the wavelength because it is the distance between two consecutive compressions. So the correct options are A is rarefaction and B is wavelength. 6.2 is a combination of AO2 and AO1 question, and this question is from the properties of the waves. The wave shown in figure number 8 has a frequency of 4 kHz. Calculate the period of the wave. Here the period means the time period, and the time period is represented by capital T. We know that frequency is 4 kHz. We need to convert kilohertz into hertz, and we know that kilo means 1000, so frequency is 4000 hertz. We also know that the time period is equal to 1 hour frequency. Our frequency is equal to 1 hour time period. We need to find the time period, so time period is equal to 1 hour frequency. So frequency is 1 over 4000. We need to use the calculator. Our answer is 0.00025 seconds. So the time period of the wave is 0.00025 seconds. The mark distribution is given along each step. 6.3 is an AO1 question, which is the knowledge based question, and this question is from the properties of the waves. Write down the equation that links frequency, wavelength, and the speed. So we have the formula, or we have the equation that speed of the wave is equal to frequency of the wave times the wavelength of the wave, or V is equal to F into lambda. 6.4 is an AO2 question, and this question is from the properties of the waves. A sound wave have a frequency of 300 Hz, travels through the air. The air has a temperature of 28 degree. Determine the wavelength of the sound. We have the formula that V is equal to F lambda. We need to find the wavelength. We have the frequency, but we don't know the speed. We need to use the figure number 9. We need to use the temperature 28 from the figure number 9 to find the value of speed of the wave. Let's see the figure number 9. In figure number 9, for the temperature of 28 degree, we will draw the straight line up to the graph, and from the graph we will go on the left side. The speed of the wave at the temperature of 28 degree Celsius is 348 meter per second. So we have the speed 348 meter per second. By using the graph, we got the speed of the wave that is 348 meter per second. We will use the formula V is equal to F lambda to find the wavelength of the wave. Let's see the model answer. V is equal to F into lambda. The speed of the wave is 348 meter per second. The frequency is already given, that is 300 Hz. We need to find the lambda. Question number 7. Figure number 10 shows competitors in the wheelchair race at London Marathon. The distance of the London Marathon is 42,000 meters. We can see here the different competitors are competing with each other in the race. 7.1 is an AO1 question, and this question is from the topic of work done and the energy. Write down the equation that links the distance, force, and the work done. Students must remember the formula, or they can use the equation sheet to find the formula which can link the work, force, and the distance. The correct formula is work done is equal to force into distance. So W is equal to force times distance, and distance is represented by small s. 7.2 is an AO2 question, and this question is again from the topic of work done and energy. During the race, the competitor works against the air resistance. The work done against the air resistance by the winner of the race was 3.36 million joules. Calculate the average air resistance acting on the winner of the race. So we need to find the value of the force because air resistance is a force. So the amount of energy or the work done that is given here, the distance traveled by the competitor that is 42,000 meter in the race. We need to find the air resistance. We will use 7.1 and we will use the formula work is equal to force into the distance to find the air resistance. Let's see the model answer. We know that work done that is equal to force into the distance. The value of the work done, which is already given here, that is 3.36 million. We will use the value of the work done and the distance traveled in our formula. By using the value of the work done and the distance traveled, we can find the value of the force. Rearrange the formula with the help of the calculator. We can see that force is equal to 80 Newton. 7.3 is an AO1 question, and this question is again related to the formula. Which equation links the distance traveled, speed, and the time? Student can use the equation sheet to find the relationship or equation between the distance traveled, speed, and the time. From our triangle formula, we know that distance is equal to speed into time. 7.4 is an AO2 question. The distance traveled of the London Marathon is 42,000 meter. The winning time of the race that is 5600 seconds. Calculate the average speed of the winner of the race. So we need to find the average speed. We have been given the time that is 5600 seconds. The distance traveled is 42,000 meter, which is already given in the beginning of the question. We need to find the average speed. So we can use 7.3 to find the value of the average speed. Let's see the model answer. In 7.3, we use the formula that distance traveled is equal to speed into time. The distance traveled is 42,000 meters. Speed we need to find, and the time taken that is given here 5600. So we will use both the values in our formula. By rearranging the formula, we will get 42,000 over 5600. By using the calculator, we will get the answer. Speed is equal to 7.5 meter per second. The marks distribution is given along each step. 7.5 is an AO3 question. The student need to explain the answer. And this question is again from the topic of speed. Explain why the speed of a competitor changes during the race. From figure number 10, we can see here the competitors are on the wheelchairs. In the start of the race, all the competitors are accelerating. It means the speed is high in the beginning of the race. We also know that the road is not flat, therefore the speed will somewhere increases or somewhere it decreases. There is a friction between the road and the tire which decreases the speed of the competitor during the race. As the competitor is moving around the corner, the speed will decrease around the corner. In the start of the race, all competitors are accelerating, means the speed is increasing in the beginning of the race. The road is not flat, it means the uphill and downhill of the road. Therefore, the speed of the competitors is keep changing during the race. When the competitor is going uphill, it means the speed is decreasing. When the competitor is going downhill, it means the speed is increasing. When the competitors are moving around the corners or the bends, their speed is decreasing because they are slowing down while moving around the corner. There are resistive forces, means the friction between the road and the tire and the air resistance on the competitors, which is making the competitors slow during the race. Student can add extra points or they can use these options in the answer. The tire of the wheelchair may get punctured, making the wheelchair slow. Near the end of the race, the competitors will get tired and the speed will decrease. The competitors sometimes sprint during the race, which means that the speed of the competitors will increase during sprinting. Question number 3. Figure number 4 shows a child playing with a toy train. The train is on the bridge. When the child lets go of the train rolls down the bridge. You can see here, if we roll down the bridge. 3.1 is an AO2 question, and this question is from the topic of momentum. The momentum of the train at the bottom of the bridge is 0.216 kilogram meter per second. The mass of the train is given, that is 180 grams. Calculate the velocity of the train at the bottom of the bridge. We need to find the velocity of the train at the bottom of the bridge. We know that the mass of the train is given 180 grams. We need to convert grams into kilograms. We know that 1 kilogram is equal to 1000 grams. We will divide the mass 180 grams by 1000. Our answer is 0.18 kilograms. The momentum is given 0.216 kilogram meter per second. We need to find the velocity. We know that momentum is equal to mass into velocity. Let's see the model answer. P is showing momentum, so momentum is equal to mass into velocity. The mass of the train is 0.18 kilogram and momentum is 0.216. We will substitute both the values in our formula. We will use the mass 0.18 into our equation, whereas momentum is given 0.216. We will substitute in our equation here. By substituting the value, we have 0.216 is equal to mass, that is 0.18 times the velocity. By rearranging the formula, we will get that velocity is equal to 0.216 divided by 0.18. With the help of the calculator, we will find that velocity is equal to 1.2 meter per second. The velocity of the train at the bottom of the bridge is 1.2 meter per second. The marks distribution is given along the steps. 3.2 is an AO1 question, and this question is again from the topic of momentum. The train collides with a stationary carriage on the track. You can see here, as it is rolling down, it is going to collide with a carriage which is stationary at the bottom of the bridge. Explain why the velocity of the train after the collision is less than it was before the collision. Use the idea about the momentum in your answer. From the figure, we can see when the train is rolling down, it has velocity, so it has momentum. Whereas the carriage is stationary, it has mass, but velocity is zero. Therefore, the momentum before collision, that is also zero. When this train is rolling down, it is going to collide with the carriage. The carriage will start moving, so it will gain some velocity. So it means that it has some momentum. So momentum of the carriage is not zero. On the other hand, the train after the collision will get slow. It means that its velocity is getting slow and it loses the momentum. But the law of conservation of momentum says total momentum before collision and total momentum after the collision always remain conserved. Let's see the model answer. The carriage is stationary, therefore its momentum is zero. But after collision with the train, its momentum will increase as it gains momentum after collision. Since momentum is velocity times mass, after collision the velocity of the train will decrease. Therefore, the momentum of the train will decrease. The mass of the train is same, but the velocity will decrease. Therefore, the momentum of the train will decrease after collision. On the other hand, the momentum of the carriage will increase because it gains velocity. But the total momentum of the system always remain conserved. It means the momentum before collision and momentum after collision, it always remains same for the system. Question number 4. A teacher demonstrated the motor effect. Figure number 5 shows the equipment used. We can see here a permanent magnet. A wire is present which is carrying the current. 4.1 is an A1 question, and this question is from the topic of magnetism. Explain why there is a force on the wire when there is a current in the wire. When the current is flowing through the wire, why there is a force acting on it. We can see here a permanent magnet is present. The field lines start from the north pole and ends at the south pole, whereas when the current flows through the wire, the circular field lines are produced around it. When these two field lines interact with each other, as a result of that, a force is generated on the wire. Let's see the model answer. The permanent magnet has magnetic field starts from the north pole to the south pole of the magnet, which is shown with the help of the blue arrow. The arrow is from the north pole to the south pole of the magnet. When the current flows through the wire, it produces the magnetic field in the form of circular rings, which we can see here. A force is created as these magnetic fields interact with each other. 4.2 is an AO1 question, and this question is from the topic of Fleming left-hand rule. Explain how the direction of the force on the wire can be predicted. Students, they don't need to give the direction of the force on the wire. The question is how the direction of the force can be predicted on the wire when these two magnetic fields interact with each other. In Fleming left-hand rule, we know that if we stretch the index finger, middle finger, and the thumb, that they are at the angle of 90 degrees, then the thumb is given the direction of the force, whereas the extended index finger or the first finger give the direction of the magnetic field, whereas the direction of the middle finger gives the direction of the current. Let's see the model answer. The Fleming's left-hand rule will help to find the direction of the force. The direction of the first or index finger is in the direction of the magnetic field, and the magnetic field lines are always from the north pole to the south pole of the magnet, and the second or the middle finger is in the direction of the current. The stretched thumb will give the direction of the force, and the force is due to the interaction between the fields. The index finger, middle finger, and the thumb are all at the right angle to each other. 4.3 is an AO1 question. Figure number 6 shows a simple electric motor. You can see here a battery is present, a coil is present there, and a magnet. Explain one way the motor could be changed to increase the rate at which the coil rotates. We know that the coil consists of the turns. If you increase more turns in the coil, then it means that more magnetic field is produced around it. If you use a stronger battery, it means it will generate more potential difference or the current in the coil. If you use a strong magnet, it will produce strong magnetic field around it. When this magnetic field interacts with the magnetic field produced around the coil, the movement of the coil will increase as the result of interaction between them. Let's see the model answer. Add more turns of the wire on the coil because it will produce more magnetic field around it. Use strong battery to produce more potential difference or the current. Use a strong magnet. A strong magnet will produce a strong magnetic field around it. When these two magnetic fields interact with each other, it produces strong force and increases the rate of rotation of the coil. Question number 5. A student investigated how the color of a surface affects the amount of infrared radiation the surface absorbs. Figure number 7 shows the equipment used in this process or in this investigation. A timer is given, infrared radiation lamp is available. Two flasks are used having different shapes and colors. The method is given below. Pour water at 20 degrees in each flask. Place a bung and thermometer into each flask as shown in the figure number 7. Place each flask in front of the infrared lamp so that the radiations can fall on these flasks. Measure the temperature of the water every 30 seconds for 10 minutes. This question is from the topic of the properties of electromagnetic waves. 5.1 is a combination of AO3 and AO1 question. Explain two improvements to the method the students used. We need to explain what the improvements the student should bring in his experiment or in the investigation. The student need to place both the flaws at equidistance or at the same distance from the lamps because both of these lamps can get the equal intensity of the light. Use the flaws of the same shape and the size so that both the flaws have the same surface area. We can see in figure number 7 both the flaws have different shapes. Use the same volume of water for the both of the flaws because the rise in temperature is affected by the volume of the water. Let's see the model answer. Place each flask at the same distance from the lamp so that each flask would get the same amount or intensity of infrared radiation from the lamp. Use a flask of the same shape and size so both the flasks have the same surface area. The student can use another option, use same volume of water for both of the flasks because the rise in temperature is affected by the volume of water in the flask. Figure number 8 shows the results of each flask. We can see the graph of the white flask and the graph of the black flask. The rise in temperature is along y-axis whereas the time taken that is along x-axis. 5.2 Complete the sentences. After 100 seconds, the temperature difference between the black flask and the white flask was dash degrees Celsius. We need to use figure number 8. In figure number 8, at 100 seconds, we know that the temperature of the white flask is about 24 degrees Celsius. If we go further straight up to the black flask, we know that the temperature of the black flask is 31.5 degrees. The temperature difference is 31.5 minus 24, that is 7.5 degrees Celsius. So the temperature difference between the white flask and the black flask after 100 seconds is 7.5 degrees Celsius. The temperature of the white flask stopped increasing. The temperature inside the black flask continued to increase for a further dash seconds. We need to go back to figure number 8. In figure number 8, we can see here the temperature of the white flask stopped increasing at a time of 200 seconds, but the temperature of the black flask is keep increasing and it stops at the time of 440 seconds. The time difference, that is 440 minus 200, that is 240 seconds. So the temperature of the black flask keep increasing more than 240 seconds than the white flask. The temperature of the white flask stopped increasing. The temperature inside the black flask continued to increase for a further of 240 seconds. 5.3 is an AO3 question. The initial temperature of absorption of infrared radiation by the black flask was greater than the initial rate of absorption by the white flask. How does figure number 8 shows this? We need to use the figure number 8 and we will check the steepness or the gradient of the graph. In figure number 8 we can see here the steepness or the gradient of the black flask is very high, which shows that it is absorbing more radiation as compared to white flask. When it absorbs more radiation, therefore the rise in temperature of the black flask is very much higher as compared to white flask. So figure number 8 shows that the gradient of the line of the black flask is much higher as compared to that of white flask. Let's see the model answer. The gradient or steepness of the line of the black flask is greater than the white flask. The temperature rise of the black flask is greater than the white flask. 5.4 is an AO3 question, and this question is again from the topic of electromagnetic radiations. Explain why the temperature of water in the flask increased and then become constant. We need to use the figure number 8. From figure number 8, for both of the flaws, white flaws and the black flaws, we can see here the temperature is increasing and gradually the graph is becoming shallow or flat. It shows that initially the temperature of the water inside the flask is increasing, but later on the temperature of the water inside the flask is not increasing anymore and it is becoming flat. It shows that the water inside the flask is absorbing the radiations from the lamp and they emit the radiation to the surrounding. So the rate of absorption is higher as compared to rate of emission. When the rate of absorption is taking place, it means the temperature is increasing. But when the rate of emission is also becoming equal to rate of absorption of the radiation, so the graph is getting flat, which shows that the rate of absorption of the radiation by the water inside the flask is equal to the rate of emission of the radiations to the surrounding. Let's see the model answer. The flask absorb the radiations from the lamp and emit the radiations to the surroundings. Initially, the rate of absorption of the radiation is very higher than the rate of energy transfer to the surroundings. Because the water is at the low temperature, therefore the energy is used to increase the temperature of the water in the flask. When the temperature of the flask, means the water in the flask, increases enough, then the flask transferring the energy to the surroundings. A time will come when the rate of absorption of the radiations by the flask will become equal to the rate of transferring of the radiation to the surroundings. Therefore, the temperature of the flask stop increasing. Question number 6. The distance a car travels during the driver's reaction time is called thinking distance. 6.1 is an AO2 question. Figure number 9 shows how thinking distance depends on speed for a car, and this question is from the topic of speed, velocity, and acceleration. Figure number 9 shows the relationship between the thinking distance in meters and the speed of the car. It is a straight line passing through the region. We know that the distance is equal to speed into time. We can determine the driver's reaction time. We need to find the time. So from our graph, we need to find the value of the distance traveled at a specific speed or velocity of the car. Student can use any point from the graph. So it is easy for the student to find the distance traveled or the thinking distance for the speed of 10 meter per second, which is 7 meters. So the speed is 10 meter per second and distance traveled with the help of the graph, that is 7 meter. We need to find the reaction time. We know that the time is equal to distance over velocity. We can use the equation sheet to find the formula to find the reaction time. Let's see the model answer. Distance is equal to speed into velocity. We know that the distance traveled for the speed of 10 meter per second is 7 meter. We will use both the values in our formula. So 7 is equal to 10 into time. By rearranging the formula, we know that time is equal to 7 over 10 and that is equal to 0.70 second. So the driver reaction time is 0.70 second. 6.2 is an AO2 question, and this question is again from the topic of speed. Figure number 10 shows how the velocity of a car changes during braking. We can see here the speed of the car or the velocity of the car is 30 meters per second, and the driver starts applying the brake. The speed of the car is keep changing and gets stopped at a time of 5 seconds. Determine the braking distance of the car. We need to find the braking distance with the help of figure number 10. In velocity time graph, the distance traveled is always the area under the graph. So the area under the graph is given here. With the help of these square values, we will try to find the area under the graph. To help the students, we can see here that different parts of the graph are highlighted with different colors. To find the squares under the graph, we can see here the number of squares are 1, 2, 3, 4, which are complete square, whereas the area of one square is 5 into 1. 5 is along y-axis and 1 is along x-axis. So we need to count the number of the squares 1, 2, 3, 4. And if you look here, it is not a complete square, but some part is already given here. So I highlighted for the student with the same color. So it will become easy for the student to count the number of the squares. So 1, 2, 3, 4, 5, 6, 7, 8. Student can count 8.5 or 9. So the number of the square under the curve are between 8.5 to 10. We know the area of one square, that is equal to 5. Therefore, we will time 8.5 and 9 with 5, and we will find the area under the curve. Let's see the model answer. We know that the area of one square means the distance traveled, that is equal to 5 times 1, that is equal to 5 meter. The unit of distance traveled, that is in meters. So number of the squares from our graph or from our figure is 8.5 to 10. So the total distance traveled by the driver or by the car is 8.5 into 5 is 42.5 meter before it gets stopped. The acceptable answers are 42.5 meters to 50 meters. So we need to use the figure number 10 to find the area under the graph. 6.3 is a combination of AO3 and AO1 question. Explain how the gradient of the line on figure number 10 shows that the resultant force on the car was not constant. The concept of the resultant force is from the Newton's second law. For the resultant force, the acceleration is always present. From figure number 10, we can see here the graph is not a straight line. If the graph is a straight line, it means the velocity is changing constantly, therefore it produces a constant acceleration. But on the other hand, we can see here the graph is a curved graph. The change in velocity with respect to time is not constant. It means the acceleration is produced, it is not a constant acceleration. If the line is a straight line, it shows that the change in velocity is at a constant rate, or the gradient is constant. If the gradient is not constant, it means the acceleration is not constant. If the acceleration is not constant, it means the force is present which is responsible for change of acceleration. For the constant acceleration, student must remember the line must be a straight line. It should not be a curved line. Let's see the model answer. The gradient means change in y with respect to change in x. And change in y from our figure number 10 is velocity, and change in x is time. We know that change in velocity with respect to time is called acceleration. The gradient from the graph in figure number 10 gives acceleration. The graph is not a straight line. It means the value of the gradient from the graph is not constant, which means acceleration is not produced at a constant rate. If acceleration is not constant, it means the resultant force is not constant. From Newton's second law, we can understand if the acceleration is not constant, it means the resultant force is also not constant. Question number 7. Figure number 11 shows a stationary apple hanging from a tree. The X marks the center of the mass of the apple. 7.1 is an AO1 question. Draw two arrows on figure number 11 to show the forces acting on an apple. We know that the apple is hanging, so its weight is downward due to the pull of the earth. So the weight is towards the earth, but it is now falling down. It means there is a force which is acting on apple which is in the upward direction, and that force is due to the support given by the tree. So one force is acting downward at the point X, which is downward force due to the pull of the earth, which is called the weight, W is equal to mg, whereas an opposite force is present there, which is coming as a support from the tree. So the two forces are there. The student need to draw two arrows which are of equal length, and they will start at the point X. So the model answer is the red arrow shows the weight of the object which is acting downward, W is equal to mg, whereas the upward force is the support given by the tree. So these two arrows must be of the same size and in the opposite direction and acting at the same point, that is point X. The weight is represented by the red arrow which is towards the earth, whereas the blue arrow is equal in size to the red arrow and it is the support given by the tree. 7.2 is an AO2 question. It takes 0.5 seconds for the apple to fall to the ground. The initial velocity is given 0 meter per second. The value of g is given, that is 9.8 meter per second square. Calculate the distance fallen by the apple. The student need to find the distance, and distance is represented by s. We have the time, we have the acceleration due to gravity. The value of g is 9.8 meter per second square, and the initial velocity is given, that is 0. So we need to use the Subat equation, and we need to find the value of s. We have the value of g, we have the value of initial velocity, that is 0 meter per second, but we don't have the value of v, which is the final velocity. So first of all, we need to find the final velocity. To find the final velocity, we use the formula of acceleration. Let's see the model answer. We know that acceleration is equal to change in velocity over time. Change in velocity means the initial velocity minus final velocity. Then we can find the value of v, and we can use that value in our formula. In Subat equation, v square minus u square is equal to 2gs. By substituting the values in this formula, g is 9.8 because it is acceleration due to gravity, means the acceleration produced in the apple due to the pull of the earth. Change in velocity mean v minus u, final velocity minus initial velocity, and the time is already given, that is 0.5 seconds. By rearranging the formula, this 0.5 is going to multiply with 9.8. We will substitute the value of u, that is 0, so we will get the value of v. By using the calculator, we will get v is equal to 4.9 meter per second. The Subat equation is v square minus u square is equal to 2gs. Student can use the physics equation sheet to find the formula for the question. V is equal to 4.9. So 4.9 square minus 0 square is equal to 2 into 9.8 into s. By using the calculator, we will find that it is equal to 19.6. It will go on the other side and will divide 24.01. The value of s, that is equal to 1.225 meter, or the student can write the distance traveled by the apple is 1.2 meter. 7.3 is an AO1 question. In question number 7.2, it was assumed that acceleration was constant, that 9.8 meter per second square. Evaluate this assumption. We know that when the apple will drop from the tree, it starts moving downward towards the ground. It means two forces are acting on it. One is the weight which is acting downward, and apple is moving downward towards the earth. But on the other hand, opposing forces are present there on the apple which are acting in the opposite direction to the motion of the apple, that is the air resistance. So as the speed is increasing, the air resistance also start increasing. So the resultant force is the difference of these two forces. If the resultant force is present there, then according to Newton's second law of motion, the acceleration is present and the acceleration is not constant. So assuming that the acceleration due to gravity was constant throughout the journey, that is 9.8 meter per second square, is not a correct assumption. Let's see the model answer. 7.3 is an A1 question, and this question is from the motion along a line. The first possible answer is as the apple falls downward due to its weight or the pull of the earth, the air resistance will start acting on it, which is already mentioned here, in the opposite direction to the motion of the apple. Therefore, a resultant force is acting on the apple, which is the downward force minus the air resistance. Therefore, the value of the resultant force will decrease. It's not only the weight, but also the opposite forces are present there, which is the air resistance, which is acting in the opposite direction. Therefore, the resultant force is decreasing, means the acceleration of the apple is not constant. According to Newton's second law of motion, if the force is not constant, the acceleration produced in the apple is also not constant. As the acceleration is not constant, therefore the above assumption that the acceleration is constant throughout its fall is not a good assumption. The second possible answer for the same question 7.3 is if the ground is very close to the apple and the apple travels a very small distance to reach the ground, in that case the air resistance is negligible. So it will fall down and there is no impact on the resultant force. The force is almost constant, therefore the value of g is constant throughout the journey. Then it is a good assumption. Let's see the model answer. If the apple travels a very short distance through its journey, it means the air resistance on the apple is very small, means negligible, or you can say that no resultant force is acting on the apple. If there is no resultant force, it means there is a constant acceleration while falling down towards the ground, so it means there is no change in acceleration of the apple. Therefore, the concept of the constant acceleration is a good assumption.